Hello and welcome to my video, lesson 6.5 on the financial implications of exponential functions. So we're taking a look at compound interest because compound interest is exponential, which is amazing because if you've noticed any trends in our exponential growth graphs, you'll hopefully have noticed that the trends are pretty staggering. They grow ridiculously well. Not exactly like this, but like they grow quite well. Like, right? They start trending up, and as they start trending up, they trend up more and more and more and more, and they grow a lot faster. Which is also why, generally speaking, people that are older, if we think about this as age, right? When you're zero, you don't have very much money, but when you're older, you generally speaking have a lot more money. Not because older people are mean or because they're evil people because they have money or something. It's just as you get older, you earn money and you invest it, and so you get more money. Having money gets you more money. So it's kind of a painful process, but you can imagine that if you're 80, you have a whole ton more money than if you're 0 and if you're 18 here at the beginning, right? Or you can if you invest it properly. Okay, so that's pretty cool because no matter where you are right now, if you invest your money properly, especially at a younger age, you can actually get a lot of money over time. So the more money you save at a young age, the more money you have when you're older. So compound interest is exponential. The benefit of compound interest. So let's take a look at an example question here. We have $100 at 10% in simple interest over 5 years. So simple interest is just that, it's simple, right? So if we want to calculate the interest, we put in the principal times by the percent, or we can write down the percent as a decimal, and then times by the time period, so 5 years. So if we do that here, that means we're going to have $50 of interest over 5 years. Okay, so that's not bad, right? That's pretty good. Okay, but it's not amazing when you compare it to compound interest. So the same numbers, right? 110 over 5 years, what are we going to get? Well, if we start at the first year, this is what compound interest does. It takes the first year and you multiply it by getting your new percentage, right? So it's 110% of the old amount, right? So after the first year, you're at $110. Then you multiply it again. So this is our second year. We do that again, and now we're at, well, now I'm going to have to start typing it in here, times by 1.1. Now we're at 121. After the second year. After the third year, we're going to do it again, times by 1.1. Now we're at 133.1. We're just going to do it again, times by 1.1. Now this was, let's just be careful here. This is year number 1, this is year number 2, number 3, number 4. So now we have, I'm going to get rid of all this age stuff, who cares? Now we have 146.41, and we're going to do it again for our 5th year in a row. And so what are we going to get? So after we do that for a 5th time, now we get 161.051. So after 5 years, instead of getting $150, we got $161. So it's a significant improvement. And this is a reasonable, 10% is a reasonable compounded interest amount. So it does add up, and it actually benefits over time more and more and more. And the longer you go into the future, the better it's going to be. Let's just imagine, so if you go back and look at our first topic, or first two topics, we remembered that if we multiply by the same number over and over again, that's our pattern, then what does that mean? Well, that's going to be the base of our exponential function. So if we write it down like this, and the starting position is going to be the a value, and we're going to put x up here. So this is actually the function that models the situation I just made up. So this function right here models the situation we just did. Actually, speaking of which, I should turn off the stat plot. I should go zoom 6 and see what happens. Oh, it's not big enough because I have to have a I need to have a y value of at least 100, and it's growing from that. So let's make it 250. There you go. So you can see this is after 10 years, it gets to almost $250. So you can see at different points it's growing to a different amount. The y-axis here on this side is your total money. It's your money. And then the bottom x-axis is your time. So this is the formula. A is the future value, the value at some given point in the future. P is your principal, that's the starting value, that's in this case 100. And then you go 1 plus I being your interest rate. So in this case 1 plus 0.1, so that's why we have 1.1. And then we have n, which is the number of compounding interest periods. All right, so before we continue, we do need to know a few words and what they actually mean. So for example, we need to know the number of times per year. So if we are talking about compounding periods, and we say it compounds daily, well, this does make a huge difference. So it compounds 365 times per year if it's daily. It's 52 times if it's weekly. Bi-weekly means we cut that in half, so 26. Monthly means 12. Semi-monthly means twice a month, so you multiply that number by 2. Quarterly means 4 times a year. Semi-annually means twice a year. Annually means once per year. So these are just definitions. Okay, you'll have to remember them. Okay, with all that in mind, we're going to try to do 2 questions here. Jimmy invests $1,500 or $1,500 in an ETF with a historical 12% returns. If the returns stay the same, how much does he earn over 5 years if it is compounded annually? So first of all, our formula is that we need our principal and our rate of return, so 12%, so we're adding 1 plus the 12%, and then the number of terms, so 5, number of compounding periods, so 5. So all we have to do is plug this into our calculator. So we have 1,500 times by 1.12. Oh, we don't want alpha. Now I've screwed it up. There you go, 5. Now we press enter, and we have 2,643.5. And this is after only 5 years. And it's almost doubled, which is amazing. With 12%, it almost doubled in just 5 years. Okay, what about if it's compounded quarterly? Well, if it's compounded quarterly, what are we going to do differently? Not much. But we are going to, if it's 12% quarterly, that means it happens 4 times per year, so 5 times 4. So it's going to be the same equation as before, but it happens 4 times per year. Whoops. 4 times per year. So now it looks like it doesn't do a lot in our equation, but the exponent is so much higher, and so our value is so much higher. So this is $14,000, much higher. So at what point would annually catch up to that number? Well, in 20 years, right? So if it was compounded annually, this number would have to be the same. So it'd have to be 20 years. All right, let's take a look at one last question. If Bob invests $5,000 into mutual funds, which have a historical 8% return compounded semi-annually, if the returns stay the same, how long until Bob doubles his original investment? Okay, so there's a few different parts here, but let's first of all make ourselves a equation. So we have the principal, which is 5,000. We have the historical return, which is 8%. So that's what I just wrote down. And so we have our n up here. Okay. So how long till it doubles the investment? Well, what's double of 5,000? Well, double is just times by 2, so 10,000, right? Double. Okay, so let's take a look at how we can solve this. Well, what we're going to do is go 5,000 and write in our equation. Okay, and we're going to write in our second equation, which is 10,000. And we're going to graph them. Actually, we're going to zoom out a little bit. We want to double it, so we need to get to 10,000. So let's go and get to there. So 500. And let's see what that looks like. Ah, there you go. Perfect. So now that point at which the blue line is at 10,000 is our is that year. So intersect, let's find it. So we want to go all the way over to the point. So first and second line, and then we guess at that point. And it says after 9 years, so after 9 years, that's the x value that it's returning here. After 9 years, it is doubled. Which is pretty amazing. All right. I hope that this video helps you understand financially exponential functions a little bit better. And good luck.